Everybody, as always, my name is Joe and I'm the team lead.
My name is Cassandra and I'm the recorder.
I'm Zach, I'm architect.
I'm Beck and I'm our customer communicator.
And I'm Logan, our team's quality controller.
We're team Glacies Indicium. Our client is primarily Dr. Salvatore with NAU and our faculty mentor is Rue Abraham. Our clients are made up of geologists and data scientists who are currently working on surveying and mapping the entire continent of Antarctica using satellite imagery, what end up being represented as raster images. Quick run through from last time. An image on your computer is typically 3 bands, a red band, a blue band, and a green band. A raster image isn't limited to a number of bands, but can also be coordinated to actual lat-long coordinates on Earth. In some cases, the raw images our clients are working with only have 8 bands representing different ranges of the electromagnetic spectrum. Simplistically, we see a small range of light in the spectrum, but we can still collect data from other ranges of the spectrum. In other cases, our clients have done different math and analysis with this raw data to compute and derive bands, modeling landscape data such as presence of snow, shadows, ice, and even certain rock types. The main problem is that it's easy for a scientist to examine one image at a time, which for reference and size is around 2 gigabytes on average, but it's impossible to interact with the data on the continental level, as it can take up to multiple petabytes. Ideally, a geologist wouldn't want to see just a small area of land cover like this, but would want to visualize a map of a larger region. This lets them gain a greater insight for further expeditions, as well as into data on the continental level. Using geographic information system software like Google Earth and ArcGIS, they can represent these different wavelengths of the landscape data or the landscape data that they generate. Using different combinations of the spectral wavelengths, they can map what it would look like in real life, such as on the left, or they can map single bands, or in this case, multiple bands of landscape data seen on the right. So high concentrations of certain colors might mean a high concentration of something like presence of shadows or ice. This analysis is really valuable to the community as well as to the world because it helps build our understanding of one of the world's least understood continents. As climate change becomes more and more apparent, it becomes more important to understand Antarctica and how it plays into the world's Earth systems. In addition, it will expand the amount of scientists and particularly geologists that can work with this scale of data. The raw data our clients receive is proprietary, so giving scientists access to model data like we are will only further the research and expeditions that can be done on the continent. Our outline solution overview is split into 2 parts. The first of which has to do with a few pre-processing steps on the raster images we've received. First, a raster image typically covers around a square mile. To be more useful, we would want the data to be visualized not a single image, but to make up an entire region. From there, we're using an open source base, Terracotta, to place raster images onto a map of Antarctica, but it only accepts single band images. And as I've stated, the images we're working with are at a minimum of 8 bands. This leads us to having 3 steps in the pre-processing stage. In summary, we have to determine whether an image falls into a particular region, make a mosaic of said region, which is just a fancy word for a collage of raster images. And then finally, we have to split each mosaic up into its respective bands to be properly ingested by the front end to be visualized by the user. The other main part of our solution overview primarily deals with the user's perspectives and highlights the key features of our graphical user interface. As I've said, Terracotta ingests the pre-processed images that we feed into it, and from there, we have a set of features we're actively implementing to realize our client's desired experience. The map interface is responsible for the navigation of the data and to get our clients and to get a holistic view of what is being displayed, In addition, our clients would like a way to query the database to find areas of a large concentration of a particular data type. Filtering and selecting different band types and regions is actually well into implementation as it is an expansion of the utilities Terracotta already offers. Finally, this all should be easily accessible to our clients via a web application, which will also have the ability to export sections of the data and the map to the client so that they can utilize what they're working with elsewhere and in other forms of graphical information systems.
We established many requirements last semester. We needed to have a A map of Antarctica with raster image overlay. This map also needed the ability to filter by band and by region. We needed to have a backend database that would allow for both raster image viewing and exporting. Next. This semester, we broke down these requirements into 3 different modules: pre-processing, the backend, and the front end. Our pre-processing module must take a folder full of GeoTIFF images and break them down into at least 8 different bands, and then reassemble them by region. This way it is possible to view them on our map. Our backend is an SQL database that returns geolocated PNG arrays. The server application then sends the tiled image back to the user. Our front-end module deals mostly with our user experience. We are using a base of Terracotta and have modified it to include a list of regions found in Antarctica and a list of checkboxes so the user is able to view different rock formations. The front end also allows users to zoom in on different areas of the map to gain a deeper understanding of the whole continent.
As mentioned in the earlier slides, the implementation of this project is separated into 3 different parts consisting of the pre-processing module, the server backend, and the front-end client application. The pre-processing module will accept a file with a similar naming convention to this one on the left and will translate into a JSON file of nested objects, which represents the different nested regions in Antarctica. By using a JSON object, it allows for quicker parsing of the regions in order to create the front end with a nested region view. The pre-processing module also separates each file into different layers, which represent different geological elements in each region, such as snow or rock types. Next slide. The backend server consists of the SQLite database, which acts as a middleware between the GeoTIFF files and the front-end user interface. The backend server is created with Python in order to handle any API requests from the front end for specific information in the GeoTIFF files, which are located in the SQL database. An example of an API request is shown on the left, which provides easy and quick access to specific data in specific regions as well. This API request can also be put into the browser to view a JSON list of all the available information for each region. If the API request is successful, then data is passed back into JSON format for easy parsing. Next slide. The front end consists of 2 parts, the map and the controls on the left panel of the application. The map is created through leaflet with the ping images from the backend tile on top. The buttons on the left communicate directly to the backend server through the available keys, which were created in the pre-processing module to create the nested list. To display images like this one, only the region name and band are needed, which are passed into the API to retrieve the tiled images. Once the image is available, users can then zoom in or out or select different geographic elements from the band keys presented in the user interface, which will automatically update the layers in the map to display the new selected band.
Because of the functionality Terracotta provides to connect the backend to the front end, many of the challenges we have are regarding the pre-processing and user interface modules. On the pre-processing side, we first need to find a way to key the source images by region so that we can filter the map visualization later by those different regions. To accomplish this, we will be using a Haversine great circle distance formula, which is used to calculate the shortest surface distance between 2 locations, while also taking into account the curvature of the Earth. This will allow us to compute the distance between the center of each image and the centers of each region to find the closest region each image belongs to. Next. After this, we will need to be able to key each image by band as well. Terracotta provides functionality for keying the images, but as previously mentioned, Terracotta only allows us to visualize single band images, while our source images have multiple bands. To solve this problem, we will be utilizing raster.io, which is a geospatial data processing library built upon the industry standard file translator library known as GDAL. And this will provide the framework for processing raster images in Python. Using raster.io, we can extract the bands of each image to produce single band images that can be used by Terracotta. We can then combine these within their regions to form single band mosaics that are able to be quickly and easily served to the map application on the front end. Next. The final pre-processing challenge we have involves organizing the data so that we can have efficient and quick access to serve the map on the front end. Our solution to this is to combine the single band images of a region into a larger mosaic for that region, as mentioned before. Then we will need to organize them into a regional hierarchy system as shown in the image here. So that way the keys can easily access the images belonging to each region. Next. On the user interface side, we face obstacles when it comes to filtering and exporting. We'll be using a base map and polar stereographic projection using Leaflet, which is a JavaScript library. This will be very compatible with the JavaScript modules we will use to create the checkboxes for filtering by band and the regional hierarchy list for filtering by region. Our JavaScript module will generate a dynamic JSON file of our regions to display in a list to the user, and the bands will be accessed statically. With help of Terracotta, selecting the regions and the bands in the application will call JavaScript functions to access the keys in Terracotta for the mosaics that need to be served. Lastly, we will need to meet our client's goal of making the source data accessible to the scientific community. This is a difficulty because we need to change which data we are accessing with Terracotta and provide a link to download instead of serving it on the map. Our solution to this obstacle is to create a file naming convention and add region and band keys to the source file names in pre-processing steps. Then on the front end, clicking an export button will access a list of currently selected keys and then generate a list of corresponding file name parameters to search for so that Terracotta can trace back to the source images, compress them, and send back a download link.
So this semester so far, we have worked with our clients to finalize a complete specification for our final product. We've made significant progress toward the implementation of each component of our proposed solution, including a modular image preprocessing system written in Python and a custom user interface for navigating and interacting with our clients' processed satellite data, building on the open source raster tool called Terracotta. Going forward, we anticipate a successful completion of the modules necessary to provide a functional demonstration of the project components by mid-semester. We predict that by the end of this project and following a thorough process of system integration and documentation, our clients will receive a satellite imagery visualization tool along with a source image preprocessing system that both meets their expectations for the scope of this project and that they can apply to new satellite data sets as they continue their own work into the future. Next. Here's a quick Gantt chart describing our progress on this project visually. As you can see, we're about 2/3 of the way into the implementation phase. At this stage, the server deployment strategy is completed. Our user interface and data download functionalities are nearly complete, and our pre-processing system is still under active development. Next. In conclusion, we are Team Glacies Indicium, and our clients are planetary geologists who study Antarctic geology with satellite photography. Their source imagery contains analog sensor data like wavelength reflectance values, and from mathematical models, they can compute geologically useful information like presence of snow and shadow, and even rock types and surface composition. They study this visual data to learn more about the geology of the Antarctic continent. With this project, they're looking for a new way to share this work with the global scientific community that enables scientists around the world to contribute to our understanding of Antarctica. Our product is going to be an interactive web-based map application, which lets users navigate and interact with this huge amount of specially processed satellite data. Our project's goal is to make Antarctic geology more accessible by building a tool which makes studying the satellite data easy and fast. We've made a lot of great progress so far this semester, and at this point, we're confident that we'll be able to integrate the technologies we've discussed here into a final product that will make helpful contributions to the advancement of Antarctic geological science. And that concludes our second design review presentation. We hope this has been interesting and informative, and thank you all for listening.